Hi, welcome to Teardown Tuesday. Yes, I'm at the whiteboard. We're not going to jump in to the teardown. Thought I'd just do a little bit of whiteboard fundamental theory today, and then we jump in to the teardown and see if we can see a similar arrangement to what we get in the basic topology of, in this case, uninterruptible power supplies, or UPS. You've no doubt heard of them. You're probably using one at home to back up power your PC, for example, when the mains power fails. Then the battery inside the UPS takes over and supplies power for 5 or 10 minutes, or maybe even longer, so that you can continue to use your machine, or at least it can gracefully shut down and save your work, for example. So if the power just fails, boom, it doesn't just shut off and you lose everything. So very common device, the UPS. And there's actually three types, so basically three different topologies. There's a few more, but these are the three basic types which we'll have a look at. There's the offline standby type, probably the most popular. You'll find in the really cheap ones. There's line interactive, which is the one we'll take a look at today in the teardown. And there's the full online / double conversion type, which is the more expensive and more reliable types for the more robust applications. So if we take a look at the basic offline standby one, you're probably familiar with how they work. We've got AC mains coming in here, AC mains going out, that's it. And inside, we've got ourselves a AC to DC rectifier here. Yes, it's just a traditional bridge rectifier or whatever. And that goes into a charger, which then charges the battery. And then the battery goes into a switcher, or which is usually a H-bridge arrangement, but it doesn't have to be. But it basically is a switcher driving the primary of a transformer, and the secondary of the transformer produces your sine or your square wave out. And then they've got a basic switch in here, which can usually, this thing, by meaning offline, it means that the charger and battery part of it is usually offline. So it's switched out, and your AC is switched directly through to your output like that. So only when it detects that the main input mains power has failed does it rapidly switch over. So I haven't shown any switch in here, but it rapidly starts up the inverter in here, your step up conversion here, and generates your sinusoidal or square wave output voltage. And you can usually, it can take tens of milliseconds or 100 milliseconds or something to sort of switch over and start up. So the device that you're actually powering has to be able to handle that little sort of dropout or brownout as it switches over to the battery backup. Now that is the cheapest and most common one. Now I'll skip this line interactive one for a second, and we'll jump straight down here to the online / double conversion type. You'll see why it's called double conversion in a second. Now the difference between these two basic types is that the offline type, as I said, usually the output is powered directly from the input. It's switched straight through. So it's the battery backup part of it is offline, but you guessed it, the online type is where the battery is continuously powering the output here, regardless of what the input is doing. And that's why there's no switch going from the AC input through to the AC output, because that power is always coming, well, not necessarily coming from the battery, but actually coming from the DC rectifier down here. And you'll notice that all of the all the common components are still there. They're virtually identical. We've got our AC rectifier down here. We've got our battery charger. We've got our battery. We've got our switcher with our step-up transformer to generate either your sinusoidal or your square wave output. But you'll notice that there is no switch connecting. It can't bypass any of this stuff. It's always working. And what we're switching here, instead of switching from input directly to output, we're switching basically whether or not we want to power the output from the battery or from the rectifier circuit down here. And that's one of the big differences. One of the main reasons you want to do it is for isolation. For example, you notice that there's no direct electrical connection from the output to the input, i.e. it's galvanically isolated. So if the device you're powering needs to be electrically isolated from the input, then an online or double conversion / switcher is the way to go. But as you can see here, there's no isolation. Even though we've got a transformer in there, you'll notice that it's all commoned like that from the input to the output. And the other main reason why you want to use the online one compared to the offline is that if you've got a real noisy mains and it's always dropping, there's always brownouts and dropouts and all sorts of stuff, you don't want this thing to be continually switching back and forth between the input and the battery, for example. You're much better off on those in those noisy and troublesome environments to go for an online conversion where it's just always running from the DC here. And that's why it's called double conversion, because we're converting AC into DC, and then it's permanently, the output here is permanently running from that DC connection. It's not switching through the AC and then switching between AC and DC sources effectively. It's always powered from that DC source. And that's why they call it the double conversion, because you're converting once and then you're converting again. Yes, this one does it up here too, but there is the option to switch through with no conversion at all. Hence the name double conversion. But one of the disadvantages of this double conversion type is that, well, you notice that this switch down here is switching the relatively low voltage battery. For example, 48 volt battery might be typical. They might be using 12 volts, for example. Then lower voltage, Ohm's law still must apply, right? That means for the same amount of output power delivered to the load, you've got much higher switching currents in here. So I've shown this as a mechanical switcher relay, and the topology doesn't exactly need to be like that, but it basically means you've got very high switching currents in here that you have to switch from the battery. Up here, if you're got, say, for example, a typical 10 amp mains outlet, well, you only need a 10 amp relay in there. That's it. Not a problem. But down here, you need much, much higher currents. So the switching can be an issue down here. And also, this rectifier down here has to deliver the full load all the time, because you notice when it's not powered from the battery, it's got to deliver all that power from that poor little rectifier down in here, whereas here the rectifier is only needs to be sized enough, designed well enough to deliver enough power to charge the battery, which might be much, much less than the output load is capable of. So that's why these things are more expensive and more difficult to design. They're going to run hotter, things like that, because the circuitry inside is got to deliver that full load, and then you've got losses in there, and the switch has always got to be operating and delivering the output load. Whereas up here, your switcher or output load might only need to be sized and designed for operation for 10 minutes, 30 minutes, for example. But this thing, it's got to work all day, every day, 24/7. So this thing needs a lot more cooling and much better design system. So that's why it's typically more expensive to design an online UPS. So that brings us to the third type, which we're actually going to look at in the teardown today, is what's called a line interactive UPS. And it's essentially exactly the same as the offline standby type, but it's a bit of a compromise between these two in that, let's say you've got a mains input here, which sort of browns out or drops out a couple of times a day. You don't want the thing always switching over to battery. So instead of it switching over to battery, what they include in here, you'll notice it's virtually identical, except for the fact that in this path here where the AC is switched through, there's actually what's called an auto transformer in there with various little taps with some other switching relays in here that can then, or it doesn't have to be a relay, it can be an electronic switch as well. Then it switches between the different taps on the transformer. So let's say your mains input nominally 240 volts, it drops down to 220 or 210. Then bingo, what they might do is then switch to this tap here, which then the output voltage is going to be boosted up a bit. So you're still going to get your 240 volts out. It can compensate for small variations, 10 or 20% variations in your mains input, if the device you're powering cannot handle that. And then likewise, if the mains input here goes above what your load really wouldn't like to have, then it can switch in this tap here, it can switch over to here, and then you'll notice that the output is going to be somewhere below, because it's a different tap, somewhere below that mains input voltage. So it can accommodate both higher and lower input voltages without having to switch over to the battery backup system. So that's what a line interactive UPS does, sort of a compromise between those, and that's what we're going to take a look at now. Oops, I forgot to include that little line in there powering our AC rectifier there. But when we take a look at our teardown now, which we're going to do in a second, we expect to see all these basic components in here. We expect to see a big ass auto transformer. It's going to be big ass because it's delivering all of the full output power load, the full 2400 watts or whatever, through to the output. So that's got to be a big beast. Then we're going to have our rectifier, we're going to have our charging circuitry, we're going to have our battery bank. In the case of this one, I know it's 48 volts. Then we're going to have our switcher, most likely a H-bridge configuration. We won't know until we turn it until we actually take it apart. And the H-bridge configuration is going to have 4 large MOSFETs in there driving the primary side of the step-up transformer, which could possibly be integrated into the main auto transformer here with another tap. We'll see when we open the thing, and that's pretty much it. We expect to see some big-ass relays to switch the taps, or some electronic components to actually switch those instead. Most likely we're going to see relays in this thing, and that's what we expect to find. Will we? Only one way to find out. Take it apart. And here's what we're tearing down today. Please excuse the fact that I've got this thing on the floor. It is a massively heavy beast. It weighs more than a brick dunny, and I'm sure it's built like one as well. What it is an APC. They're a top brand in the UPS business, so we expect top quality. It's a smart UPS model 2200 XL. As you can see, a rack mount unit designed for server backups and things like that. 3-unit high rack. And yes, I scored this one from the Australian Defence Force auction that I scored a whole bunch of other stuff, as you've seen in a previous video. And this is just a front fascia panel here that just pops off to reveal the control panel here and the internal battery pack. I do have a second rack mount unit which just contains an extra 2 sets of batteries as well, and you'll see the other connector on the other side. So this one can have 3 sets of batteries hooked up to it. Its model number is SUA 2200 RMXLI to be precise, and you can see on the control panel here why it's a line interactive UPS. It's got 2 LEDs here, one to show that, look, what happens when, to show you, indicate that the mains voltage has gone over voltage, and then it needs to correct and pull it back down. So it needs to switch in that extra tap there. And then likewise down here, if the mains voltage is sagging, it needs to pull it up and correct it like that. So obviously it's switching in the taps on the auto transformer there, and there's charge level and various other stuff, bad battery, and whether or not I think that LED is for comes on when it's powered from the battery. And there's some test functionality as well. It's got a Anderson connector on here by the looks of it for the battery bank, and that just swings around, and we can pull. I've undone the screws on this. We can pull this sucker out. It needs a bit of percussive maintenance, I think. Hang on. There we go. There we go. We got it. A bit of percussive maintenance, and the battery weighs an absolute ton, more than a brick dunny, as I said, and that will pop out. But the thing is, even with that, is still very heavy. So obviously there's a huge monster auto transformer in here, so we expect to find that. You can see it comes in 2 models. We've got the lower one here, the 2200 watt one. It does come in a 3000 watt one, which maximum input current 15 amps, and that's what, well, and output rating 2700 watts. This is 1980 watts, so almost 2000 watts output power. You see it does have a 15 amp mains input jack there. What have we got? A USB interface. We've got a serial port, EPO, that's emergency power off, and there's the other Anderson connector, the second one that goes off to the battery pack, the external one, which I've got 2. This, I believe, is an option slot. There's nothing underneath that, so I'm not sure what's actually installed in this thing. I haven't, actually been able to power up and communicate to it, or I haven't even tried, but there's all the output connectors. Big whopping 15 amp one, plus 8 10 amp outputs as well. All wired in parallel, of course, so of course you can't draw 10 amps from each one. You're limited to that 2700 watts total. So that's all those outputs are more for convenience sake. Alright, got my cordless drill this time to help out. There's a few screws on this thing, so let's crack it open. And as I said, what do we expect to find? Well, pretty much exactly what we saw on the whiteboard there. We expect to find a big ass auto transformer. Of course, that'll be the bulk of the weight in this thing. It'll be absolutely massive. And we expect to find a rectifier. That'll be pretty beefy to handle all the charge current for these batteries. I'm not sure what it actually charges at, but I'd expect that to be pretty darn beefy as well. Has to be, especially when it's charging external battery packs. We'll most likely find a huge H-bridge inverter in there. We'll find some massive wiring for the batteries and all that sort of stuff. And the H-bridge, because there's so much power involved, I expect the not to use a single MOSFET for each branch there. There's probably multiple ones in parallel. That'd be my guess anyway. So we'll give it a go. Alright, let's lift the lid on this thing and see what we get. No, it's nothing else holding it down. Ta-da! Oh, look at that. We have two transformers. We'll get a better look at this beast. I'll set the camera up vertical above it, but yeah, that looks very nice at first glance. Wow, beauty. Now, first of all, that was a bit of a surprise. We've got two separate transformers here. I expected one huge transformer, but I guess, I don't know, for technical or manufacturing or performance reasons, they decided to go with two separate ones. But if you'll notice that there's a huge cable over here. I love the fact that they've actually clamped that down there with a crimp lug, and they've screwed it down. You'll notice that there's no connection from basically this is the primary of the transform. Well, depends on which way you're talking about your terminology. If it's powered from the batteries, then this is the primary, and then this becomes the secondary. So we'll just call it the battery side of the transformer. You'll notice that there's a huge bridge joining those two, but there's no tap coming off that into the main circuitry. So really, it's effectively just one wind in there. So they're using this as one big transformer, so it's not a center tapped winding on that. So they're definitely using a H-bridge to do it. And if you have a look down in here, ta-da, you'll be able to see that. Here's where the wiring comes off, and once again, huge big crimp terminals screwed into what looks like the heatsink. Well, it is the heatsink for the power MOSFETs, the switching MOSFETs down in there, which we'll have a closer look. I'll get the macro lens out, see if we can get some part numbers in there, but they're also using that to carry the current down there as well. And you'll notice that there's 1, 2, 3, 4. So that looks to be correct. It looks to be a H-bridge, because that's the most typical configuration. So it looks like we're going to have 4 sets of power MOSFETs here, each on their own thing, each on their own little heatsink slash current conductor there. And you'll notice that, so these two, there's one over here, so this top one is the black wire which goes over the transformer, or one side of the transformer. The other side of the transformer goes to this part of the bridge, and then the battery will be connected to these two inner ones, and that H-bridge arrangement switches the battery and then alternates the supply onto the transformer. And we can see that H-bridge configuration on this DaveCAD drawing here. Please excuse the crudity of the model, didn't have time to build it to scale or to paint it. What we've got is 4 MOSFETs here, and you can see why it's called a H-bridge, because it looks like a H. If you take out that line there and take out that line there, it looks like a H with the transformer in the center taps there, and we've got our 48 volt battery across here, and we've got two P-channel MOSFETs up the top, or as we'll see in this case down here, we're going to have multiple ones in parallel, but it's exactly the same thing. They're just getting higher power dissipation, better power dissipation there. So basically, I won't go into H-bridge in detail, but basically you can switch pairs like that, which then you can alternate the polarity on your transformer there. So that's how you can switch it. But then if you just switch them off and on and had just a simple square wave output, which the cheap UPSs do, because when you turn on a MOSFET, you know, they've got very low on resistance, so that when you you know, if you just do a square wave output, then these things turn on hard, and there's not a huge amount of power dissipation in these MOSFETs, or they try to. You know, there's things with gate capacitance and everything else, and driving conditions. We won't go into any of that detail, but because we're getting a sine wave out of this thing, we're going to have to dissipate more power in the MOSFETs, which is probably why they've gone for the arrangement with, you know, this huge big heatsink, and it looks like they got 4 parallel MOSFETs on there as well. But you can clearly see that's the configuration we've got. We've got our transformer hooked on to 2 of the taps effectively on that H bridge, the center taps there, and then we've got our battery hooked onto these other 2 down here. If we follow the wires, we'll find that they actually, these 2 plates here go down to the battery pack. I find it rather interesting that they've got quite a hefty amount of capacitance there across the battery terminals. I'm not sure why they're doing that. They're 1500 microfarads at 75 volts. I can't get in there to see the brand at the moment, but it looks like there's 3 of those in parallel. And of course, not an ideal location being stuck between these 2 heat sinks, which are likely going to get quite hot. But as I said, only because this is not a full online UPS, this thing is not used or running 24 hours a day. So this is going to be dissipating, you know, nothing basically until you switch. Until the mains power fails, and then it switches on and then drives the transformer to power your load. And it does appear that the battery, the internal battery pack, is just wired in parallel with these cables which go off to the Anderson connector on the output. So it looks like all the battery packs, when you use the external ones, just all wired in parallel basically. And of course, we've just got our positive and negative there. There's no smarts, you know, there's no like a sense wire or anything like that. But of course, maybe if they wanted to, maybe they could be passing some sort of sense data over the power as well. I'm not sure. I haven't gone into the details of how that works. I find this rather interesting. Check it out. They've got 2 fans here. They've got a big ass one here, which is obviously blowing air directly over these large heat sinks here. So I presume that that sucker only turns on when it's actually powering the load. Then they've got a small little, you know, wimpy pissant one down here, which might be running all the time, or something like that, just to get some airflow through the system. And they've got an additional fan here, which looks like it just, yeah, I can just put my finger through there and spin it, so it looks like it's just sucking some air over the battery compartment. Now, as for the main board down here, there's just one board. It looks like it's all a combination of surface mount and through hole, just single-sided. So I'm not going to take this whole thing apart because I don't expect there to be anything on the bottom of this board of any note whatsoever. Looks like it's big enough, sparse enough for all the SMD stuff to be on top, and anything of interest is going to be on the top anyway. So we've got our mains input over here, securely clamped down to the chassis down there with earth. And remember, as I said, because this is a line interactive UPS, it is not isolated. So the transformer is an auto transformer, so the output, the mains output, is not isolated from the mains input. Anyway, if we have a look down here, I should probably get a shot of that, but you can see the flow through here. We've got our input filter here. We've got some these 5 relays. 5 relays. There's our relays used for. We're going to be switching some taps down here. So here's the anyway, it flows through. We've got some common mode choke, line filtering. We've got some more filtering. It looks like we've got a current transformer down there. And here's our output line. So it comes straight through the input, from the input straight through some filtering and some surge protection and stuff like that, and then straight off to your output connectors over there. And then we've got the switching of our auto transformer here. So it looks like these couple of relays around here, or these two, are probably your high side and your low side auto transformer switching. I can't see any electronic switching. These things are, what are they, 20 amps, I think, 20 amp relays. Mains are rated, of course, so they're definitely going to be able to do the job, and they switch the taps on the auto transformer over here. So it looks like we've only got one on the high side, one on the low side, so not particularly, they're not catering for various steps. It's basically, is it higher than a threshold? Yes, switch on a transformer and then pull the output voltage lower, and same thing on the low side as well. Got our fan outputs there. Whoops, looks like we've got a second current transformer down in there, and that's all she wrote. Let's get some close-ups. Have a look at our input circuitry down in here. We can see a MOV directly on the input there, and then we've got a classic common mode filter here, common mode choke with some filtering. Moving along, we've got a couple of extra inductors here, and then we've got some more filtering, large, huge filter caps down here, and then there's our current transformer. There it is. So, yeah, it's even labelled CT1. You can see that they've got a single wire going through a little transformer coil there, so they can just get an isolated tap off that, and they can measure the current coming from the mains input. And they've got and then we've got a bleeder resistor there by the looks of it, and then we've got ourselves another current transformer down in there that would be measuring the output current, and of course they'd be tapping the output voltage as well as the input voltage and reading those, so they can get the output power and the output voltage. So yeah, pretty obvious. Mains input here, and then we've got our the other one over here is measuring the output, and these cables here then bugger off to our output over here, and as you can see, yep, they're all wired in parallel there. So they're obviously got, so they got a separate wire there going off to the 15 amp jack, and then all the 10 amp jacks are wired in parallel, and we've got ourselves a little, well, not a little, a big ferrite. And I'd probably say that this third relay here is the one that actually switches the input directly through to the output, basically. You can tell, look, they've got these huge, beefy, well, that's actually coming from this one here. I mean, huge, beefy tracks in there. I mean, check that out. Joining and then the output, of course, big, beefy ones going over to here. So I don't know the exact topology they're actually using for the auto transformer and the power bypass, but yeah, these ones are also got beefy power tracks going through them as well. So make up your own mind, trace it out if you want to. And we've got more protection here, another MOV there and another MOV over there. So there's no shortage of protection in this thing, as you'd expect, because they actually claim it's part of the functionality of this UPS is to basically clean up your input mains waveform. It filters it, and it clamps it with some MOVs, and then with the auto transformer configuration actually can slightly adjust and correct for the input voltage. Now there's one thing that is starting to puzzle me, I'm not quite sure about, is where is the rectifier and the charging circuitry in this thing? Obviously, look, we've got two isolation transformers down in here. If we take a look at these, there they are there, but they're really small fry. I mean, not a huge amount of power at all, especially for the battery packs. So these are clearly not charging the battery packs. But if you saw our topology on the whiteboard, then that's what you'd expect. I expected another big transformer in here, and some big rectification and filtering and everything else. We've got some filtering happening over here, but it's directly across the batteries rather than at the output of any rectifier. So I don't see any power rectifier in here. These are obviously just little low power isolation transformers to power all the circuitry underneath here. So, I mean, I can take out the fan there, but I don't think there's going to be anything doing there at all. So I'm rather puzzled by that. They're obviously doing it some other way. No, they've just got some control stuff under there. No, there's nothing. So this thing is clearly not working like our classic topology we had on the whiteboard up there. There it is. Ooh, there's a new perspective. Now, I've had a little head scratch over this rectifier thing, and some people are probably screaming at me right now saying, oh yeah, it's obvious, and it is obvious when you think about what they're actually doing here, and it's rather clever, I think. This is my first thought of what they're doing, and it tips off why they've got a huge amount of capacitance in parallel with the battery here, and no other, I mean, clearly there's no other charger, power charger circuitry or rectifier. So how are they doing it? Well, they must be doing it by tapping off the output of the transformer. So the transformer is not actually switched here. They're always feeding power back through the transformer, back in the other direction, back into and using the H-bridge itself to actually charge the batteries. It's rather clever. This is the only way that they can be getting away with it, because we need a huge amount of power to charge these huge battery packs, and the only power devices in here are the H-bridge devices themselves. Actually, I probably should have a look down here. I might be jumping the gun, but what I haven't shown here on my DaveCAD drawing, what I emitted because I thought it didn't matter, is the substrate diode across each one of these, and there's going to be one of those substrate reverse bias diodes across each of these MOSFETs. I won't go into details of why, but all MOSFETs are going to have these substrate diodes in there, and when you have diodes like that in reverse bias, you can feed power back in from this transformer, and then you can actually have huge amount, large capacitance across here like this, or across there and there. You've got large amount of capacitance, and that's what we've got. We've got these three huge caps here, and I think they're feeding power back in from the transformer through the reverse bias substrate diodes, filtering that out and using that to charge the batteries. That is incredibly clever. I really like that. Now, you may or may not be able to see that, but what we've got is 4 international rectifier IRFB 4710 power MOSFETs in there. They're 100 volt, 75 amp rated, 14 milliohms on resistance, and they're clearly paralleling 4 of those up, and there's room for another 4 in there. So obviously the 3300 watt model would have fully populated power MOSFETs in there. So they're getting away with 4, and they're tapped into holes directly on the heatsink. Or, well, it's not really a heatsink, it's actually used as the main current carrier as well. Quite neat. And if you try and have a look down the heatsinks at the other ones, you can see that they're exactly the same. There'll be 2 with P-channel MOSFETs and 2 with matching N-channel MOSFETs, of course, and I don't see anything else down in there. There's no huge power diodes or anything like that sharing the heatsink, so they're obviously, there's just some caps down in there. You can see those things down there, and really there's nothing left for me to conclude except for the fact that they must be doing exactly what I said there and using the substrate diodes on here, reverse biased, to then charge up, and then they rectify that. So it's effectively rectifying the AC coming from the output. When you're plugging in the mains, it's coming back from the transformer, and they're just rectifying that and filtering that and then charging the battery from that. There's probably some, more smarts in there, of course, actually taking care of things, but that's the basic topology that they're using. And it's very clever. And if we get rid of that option slot, which literally is an option slot, and that just plugs in, that ribbon cable just plugs in there. It's not populated in my unit, but you can get like, I believe you can get like Ethernet interfaces and various other management modules and things to plug into. And as you can see, it looks like we've got a socketed micro there. I'll maybe try and get a close-up of that. Looks like we've got a USB capable micro here. It's a dead giveaway. It's right next to the USB. We've got an RS-232, you know, probably a Maxim serial driver in there. And that's about all she wrote. Not a huge amount of control. You know, we're obviously going to have some analog to digital converter stuff around here to measure your voltage coming from your the current transformer, and also measuring the mains input and output voltages as well to try and track that power, and of course the battery management charging capability as well. And for those who absolutely must know what the main processor is, I peeled off the sticker there. It's a Philips 87C51 Classic. Now, I was curious about how that charging system worked, so what do you do when you want to find out info on how something works? Well, look at what we have here on the back. US patent number 5,302,858. Let's look it up. And bingo, look what we have here. Sometimes you just get lucky. Now, at best, I expected maybe to find a snippet of information on how the charger system worked in the patent application, but we haven't. Look what we've found here. Method and apparatus for providing battery charging in a backup power system. It is exactly what, and it turns out it's exactly what I thought was happening, or pretty darn close to it. So this is where I love Google Patents. It pops up, just type in Google and the patent number. Here's the patent number, and it's got all the images and the full text of the patent, and it's fantastic. I'll link this in, by the way, so that you can have a look to your heart's content. And here we go. We have some images popped up here, and they've got some prior art here. What they're showing is that this is how a traditional UPS works, with the what they call a static switch here, exactly the switch we showed on the whiteboard there. Then we've got a transformer rectifier configuration, converts AC to DC. Then we've got our battery charger circuitry, our battery, our inverter, our H-bridge, and then our output transformer powering the output. And that's the prior art. But what they've got this patent for, by the looks of it, I haven't read all the details of the patent and what everything does, but I've got the general overview of it. And look what we have here. It's the same as before. You've got your AC input here. You've got your switch, which goes through to the output, but there's no charger that we had before. There's no rectifier here, and there's no charging circuitry. And that's exactly what we found when we opened this thing. It looked like there was no charging circuitry effectively, and there was no power rectifier in there and power charger. So what they've got is the original inverter, the battery for driving the output, and what they're clearly doing is permanently connecting the output transformer. Instead of switching it between the input and this, it's permanently connected to the output, and that back feeds power into the inverter here through those body diodes of that MOSFET, and then charging the battery here. And they've got a controller circuitry to power all that. They're obviously monitoring input and output currents and voltages and everything else, but that's basically working exactly like I said. And if we take a look at this figure here, they're actually showing some of the details. They're showing an ideal transformer here, but they're obviously showing the winding inductance and stuff in there, because that obviously has something to do with it. They're storing the energy in the winding inductances in there to actually back power the charging circuitry of the battery. And look, they've drawn in the body diodes there, substrate diodes on the MOSFETs there, and that's exactly what they're doing. Now they're showing the AC input here, and if you flick it over and we rotate it, oops, there we go, then what they're showing is that they are powering the, they're taking the line output voltage and then using the winding inductance to then supply power back through those diodes. They don't show any filter caps in here, of course. They're grossly simplifying this in the patent diagram. It's not going to show anything they don't need to. But that back charges the battery, and it is very clever, as I figured. And look, they're showing various configurations here, and you'd have to look up the text, and all the individual points are numbered, so you'd have to read the text in depth if you wanted to figure out how this works, because this is how patent applications work. They obfuscate everything. They just rewrite it. They take a clear technical description from the engineer who designed this thing, and that's what patent attorneys do. They just change it into gobbledygook, but it's all eventually there in the text. So they're showing both positive and negative configurations of which MOSFETs turn on, and look, this is showing clearly this diode here is then back charging through there, etc., etc. So looks like they've got a charging waveform here. Perhaps you'd have to read the associated text. Then they've got clearly some control circuitry here. Here's the battery. They've got some other, they've got an error amplifier here with a voltage reference control, ADC, all that sort of jazz. So that's clearly the control. It looks like they got some, there we go, energy build-up state. That would be in the winding inductance. Then they've got the discharge state and energy build-up state again. And you can associate that with the text description of the system operation. And there's full resistive discharge curves and all sorts of goodness in there. So they're showing you exactly how it works. But the detail is all down here in this descriptive text. And here it is in the summary of the invention here. The present invention eliminates the need for separate charger, transformer and battery charger, conveniently used in backup power systems by utilizing the main inverter to do the battery charging. Bingo! Eliminating the separate charger lowers cost, reduces complexity and weight of the system, and improves system reliability. Because as I said, I expected there to be a fairly hefty charging transformer in there plus associated power circuitry as well, but this does away with it. Fantastic. The invention provides inherent power factor correction because without the need for any additional control circuitry, the inverter charger draws a sinusoidal, non-distorted current from the power lines. Brilliant. Another side benefit of this. And here's a bit more detail. The present invention utilizes the primary and secondary leakage reactances of the main power transformer in cooperation with the switching devices of the H-bridge inverter. Consequently, the battery pack will back bias diodes, the intrinsic anti-parallel diodes connected across each of the switching devices in the inverter bridge. Brilliant. Does exactly what I thought. But in the end, like when I thought about it for 5 minutes, it was obvious due to the lack of various components that this was exactly what they were doing. There was no other way to do it. And it also tells you the inverter may be operating in constant frequency inverter charge mode or a variable frequency mode as well, yielding a higher charge current. So they can probably chop and choose under software control what method they want to use. Fantastic. And this patent isn't new either. It dates back to 1991. It was granted in 1994, and it was done by a guy named Douglas C. Foltz. Good on you, Doug. And he worked for a company called Best Power Technology. I have no idea who they are or how they're associated with APC. I haven't checked, but maybe they got acquired, or maybe it's Doug's company. Who knows? Anyway, one smart cookie invented this, and presumably nobody in the UPS business has been able to implement this, I don't know what you would call it, reverse inverter battery charger technology or something like that. Nobody else has been able to implement it because they would presumably violate the APC patent on this thing. Or I'm sure there's people out there who use it and they don't care, and they're in another country, and well, it's real difficult and expensive to sue them. But anyway, has the patent expired? I don't know. What is it, 20 or 25 years on a patent or something? But presumably APC have been the only ones that have been able to incorporate this novel technology. I mean, there could be prior art. Just because they grant the thing doesn't mean that it's enforceable and stuff like that. If you can find prior art to beat it, then you can easily, well, not easily, still cost you a buttload of money to win any patent infringement lawsuit, that's for sure. And that's a disadvantage of these patents. You think you're protecting your design, and well, you're not, because here's all the details in depth of how it all works. So it doesn't stop anyone copying it. It puts all the info out there so that anyone in the world can copy it. But what it does do, the patent, is gives you a right to sue them very expensively if they do So there you go. I hope you enjoyed that look at a combined tutorial teardown Tuesday, I guess you could call it, where I started off with some theory. I thought, some basic theory on how these things operate. See how well a product, when you take it apart, matches the basic theory that you'd find in any textbook basic block diagram approach. And usually, it does, but in this case, it actually surprised us. And it's a good example of how and why I like taking things apart, because you often find surprises like this. I hadn't heard of this technique before, but it seems obvious with hindsight. Maybe it is widely used in the industry, I'm not sure. But anyway, that was rather interesting. I found something I didn't know. I'm going to have to read further about how all this works, but it seems to be a very clever little technique, and I bet there's a lot of people out there that didn't know about this either. So there you go. Some benefits to tearing stuff down and investigating things. I love it. And if you like the video, please give it a big thumbs up on YouTube. And if you want to discuss it, jump on over to the EEV blog forum. Catch you next time.